There are moments in history when our perspective shifts, when a new tool provides a view so profound and so clear that it forever alters our place in the cosmos. We are captivated by these great voyages of discovery, and many more are planned. To ensure you're with us for every future story from the frontiers of human exploration, we invite you to follow the channel. The tale we are about to tell is of the greatest of these instruments yet conceived. A magnificent golden eye sent to sail in the lonely darkness of deep space. A machine designed not just to look, but to look back. This is the story of an observatory so powerful, it can witness the faint, ghostly light from the very first stars as they ignited in the cosmic dawn over 13.5 billion years ago. It is the story of a quest to peer through clouds of interstellar dust that have long hidden the birth of stars and planets from our view, and to scan the atmospheres of distant worlds orbiting other suns, searching for the telltale chemical whispers of life. This is not merely the chronicle of a machine of exquisite complexity, but a human epic of ingenuity, perseverance, and collaboration that spanned decades and crossed continents. A testament to the unyielding curiosity that drives us to understand the universe and our place within it. The story of the James Webb Space Telescope is not merely the story of a machine, but of a monumental human ambition, a testament to what can be achieved when nations set aside their differences to gaze upon the heavens. It began as a grand endeavor, the product of a powerful international alliance that united the intellectual and financial resources of the National Aeronautics and Space Administration of the United States, the European Space Agency, and the Canadian Space Agency. This was not a project for a single nation. Its goals were too vast, its challenges too immense. It was conceived as the rightful heir to a celebrated predecessor, the Hubble Space Telescope, which had, for decades, redefined humanity's view of the cosmos. Yet, this new observatory was designed to be something far more profound than a simple replacement. It was engineered to be an astonishing 100 times more powerful, a leap in capability so significant that it promised to open entirely new windows onto the universe, revealing vistas that Hubble could only hint at. In honor of the formidable leadership required to turn such audacious dreams into reality, the telescope was named after James E. Webb. Webb was not an astronomer or a physicist, but a masterful administrator, the second person to lead NASA. He steered the agency through the turbulent and triumphant years of the Apollo program, understanding that reaching for the moon was as much a challenge of management and political will as it was of science and engineering. To name this next great observatory for him was to acknowledge that cosmic discovery requires not just brilliant minds, but also the steady hands that guide them. The telescope's purpose was nothing less than to chronicle the entire history of the cosmos. Its primary mission was defined with a breathtaking scope to study every phase in the epic story of our universe. Scientists designed it to be a time machine, capable of peering back through the eons to witness the very first luminous glows that ignited the darkness after the Big Bang. It would watch as these first sparks of light coalesced into the first stars and galaxies, and then trace their evolution over billions of years. It would investigate the birth of new solar systems, watching as stars and planets formed from swirling clouds of gas and dust, searching for the conditions that might allow for life. And finally, it would turn its gaze closer to home, examining the evolution of our own solar system to better understand our origins. This incredible journey of discovery began on a specific day, the 25th of December in the year 2021. On Christmas morning, from a launch pad in French Guiana, the telescope was lofted into the sky. It was carried aboard an Ariane 5 rocket, a powerful and reliable workhorse of the European space program, chosen for its precision and its to carry such a precious, heavy payload. The launch site itself, the Guyana Space Center, was chosen for a very specific and powerful reason, rooted in planetary physics. Located near the equator, it allows a rocket to harness the full force of the Earth's rotation. The planet spins fastest at its equator, providing a significant velocity boost to any vehicle launching eastward, a cosmic slingshot effect that helps save precious fuel and makes the journey into the void more efficient. Unlike its predecessor, Hubble, which circles our planet, the James Webb Space Telescope was sent on a much longer and more complex journey. It does not orbit the Earth, but instead orbits the Sun, moving through the cosmos in lockstep with our own world. Its destination was a unique and lonely spot in space, a place of gravitational equilibrium known as the second Lagrange point, or L2. This point lies approximately 1.5 million kilometers, which is nearly 1 million miles away from Earth in the direction opposite the Sun. The genius of this location, first calculated by the Italian-French mathematician Joseph Louis Lagrange in the 18th century, is that the combined gravitational pull of the Sun and the Earth creates a remarkably stable region. An object placed there can maintain its position relative to the Earth and the Sun with very minimal effort. For the telescope, this orbit is a marvel of celestial mechanics. It allows the observatory to keep the Sun, the Earth, and the Moon all in a single line behind it at all times. This constant alignment is critical, enabling the telescope to use a single massive sun shield to block out the heat and light from all three bodies simultaneously, creating the permanently frigid and dark conditions necessary for its sensitive instruments to see the faint, ancient light from the dawn of time. It is a lonely, stable perch in the vast emptiness, a silent outpost from which humanity now seeks to unravel the deepest mysteries of the universe. The Hubble Space Telescope, in its comfortable orbit, just a few hundred kilometers, or a couple of hundred miles above the Earth's surface, was a frequent host to visitors. The iconic images of astronauts performing spacewalks, carefully replacing instruments and repairing systems, became a symbol of humanity's hands-on approach to space exploration. The James Webb Space Telescope, however, was designed from the outset as a solitary wanderer. Its mission profile dictated that it would never feel the touch of a human hand after its launch. The fundamental reason for this lonely existence was its location. Its distant home at the second Lagrange point, that gravitationally stable perch 1.5 million kilometers, nearly 1 million miles from Earth, lies far beyond the reach of any crewed spacecraft developed to date. A journey of that length would be a mission on the scale of the Apollo program, far too complex and costly to be undertaken for mere maintenance. This observatory had to be perfect right out of the box, a self-sufficient marvel of engineering designed for a decade or more of flawless, independent operation. Yet, with remarkable foresight, its designers included a small concession to the future, a subtle acknowledgement that today's impossibilities might be tomorrow's routine operations. Tucked away on the telescope is a specialized docking target and refueling port. This feature was added with the hope that, decades from now, a robotic mission, an uncrewed tanker dispatched across the void, could one day rendezvous with the telescope to replenish its propellant, thereby breathing new life into the aging observatory and extending its window on the cosmos even further. Initially, the mission planners were conservative in their estimates for the telescope's operational life. The calculations were based on the amount of fuel it would need to carry for course corrections on its journey to the second Lagrange point, and for the small, periodic thruster firings required to maintain its delicate halo orbit against the gentle gravitational nudges of the solar system. The primary mission duration was officially set at 5.5 years, with a more optimistic goal of a total operational life of 10 years before the propellant was expected to be exhausted. But on that Christmas morning of its launch, the Ariane 5 rocket performed its task with a degree of perfection that bordered on the miraculous. It delivered the folded telescope into its transfer trajectory with such exquisite precision that the observatory had to use only a tiny fraction of its own onboard propellant for the subsequent course correction maneuvers. The gift from this flawless launch was time. The massive fuel savings meant that the telescope began its scientific life with a nearly full tank, dramatically extending its projected lifespan. The new estimates suggested it could have enough fuel to operate for a remarkable 20 years, doubling its expected scientific return and promising a whole new generation of astronomical discovery. Even this extended lifespan must eventually end. When the last of its hydrazine fuel is finally spent, and it can no longer maintain its precise orientation, its mission will conclude. At that point, its final command will be to perform one last, gentle burn of its thrusters, pushing it out of its stable halo orbit and into a vast, passive graveyard orbit around the Sun, where it will drift silently for eternity, a silent monument to human curiosity. The telescope's extraordinary power stems from the kind of light it is designed to see. It is not an instrument for viewing the universe in the same rainbow of colors that human eyes perceive. Instead, it is an instrument built to perceive the universe in infrared light. This is the realm of heat, the electromagnetic radiation that lies just beyond the red end of the spectrum visible to us. While our eyes are blind to it, the cosmos is ablaze with this invisible light. This ability to see in the infrared grants it two almost magical powers. First, it can pierce through the dense, opaque clouds of cosmic gas and dust that shroud so much of the universe from view. To a visible light telescope like Hubble, these nebulae are dark curtains, obscuring the stellar nurseries and galactic cores hidden within. But for the Webb telescope, this dust is largely transparent, allowing it to peer directly into the hearts of these star-forming regions, to witness the birth of stars and planetary systems up close. Second, and perhaps most importantly, infrared vision is the key to looking back in time. The universe has been expanding for 13.8 billion years, and as it expands, it stretches the very fabric of space-time. Light from the most ancient stars and the very first galaxies, light which began its journey as visible or even ultraviolet radiation, has been stretched over its eons long journey across the cosmos. This cosmological redshift has shifted its wavelength so far that by the time it reaches us, it arrives as faint infrared light. To see the dawn of the universe, one must look in the infrared. This sensitivity allows it to perceive celestial objects that are 100 times fainter than anything the Hubble Space Telescope could ever hope to detect. It can effectively witness the universe as it was just 180 million years after the Big Bang, a mere cosmic moment after the dawn of creation, when the first points of light began to puncture the primordial darkness. To achieve this unprecedented vision, the telescope had to be vast. But this colossal instrument had to begin its journey, packed within the confines of a rocket fairing, a space far too small to contain it in its final, deployed form. The only solution was an act of engineering artistry reminiscent of the Japanese paper folding art of origami. The entire observatory, from its massive mirrors to its sprawling sunshield, had to be intricately folded into a compact configuration, a cosmic jewel carefully tucked into its launch vehicle, awaiting the moment it would reach space and begin to unfold itself into its magnificent final form. The The journey from a tightly packed projectile into a fully fledged observatory was one of the most complex and suspenseful deployment sequences ever attempted. The unfolding was not a single event, but a slow, deliberate ballet of engineering that took place over the course of a month as the telescope coasted silently toward its final destination. This entire process was a gauntlet of risk, a sequence containing hundreds of what engineers grimly refer to as single point of failure mechanisms. Each of these was a critical component: a latch, a motor, a cable, a pin, whose individual failure would have rendered the entire multi-billion-dollar mission a complete loss. There were no second chances, no opportunities for repair. Every single one of these hundreds of actions, from the deployment of the solar array to the unfurling of the vast sunshield and the locking into place of the primary mirror's wings, had to work perfectly, in the correct order, in the cryogenic vacuum of deep space. It was a month of held breath for thousands of scientists and engineers back on Earth, a period of profound anxiety that finally gave way to elation as the telescope assumed its final, magnificent form. And what a form it was! When fully deployed, the James Webb Space Telescope is a structure of truly monumental proportions, the largest and most complex observatory ever sent into the cosmos. It stands as tall as a 3-story building, a towering assembly of mirrors and instruments. Its most striking feature, the sprawling sunshield, stretches out to the full dimensions of a professional tennis court, a vast, shimmering kite sailing on the solar wind. This colossal size creates an almost paradoxical image when one considers its mass. The entire observatory weighs approximately 6,500 kilograms, or about 14,300 pounds. While this sounds substantial, it is remarkably light for its scale. To put this into perspective, the Hubble Space Telescope, a much more compact instrument, has a mass of over 11,000 kilograms, or 24,000 pounds. The James Webb Space Telescope, despite being vastly larger, is little more than half the mass of its predecessor, a stunning achievement in lightweight materials, science, and engineering. This celestial giant does not operate in isolation. It is in constant communication with its terrestrial brain, its operational heart. The science and flight operations are managed from the Space Telescope Science Institute, headquartered in a building in Baltimore, Maryland. This same institution has for decades been the nerve center for the Hubble Space Telescope, and now it orchestrates the scientific endeavors of both great observatories. It is here that commands are formulated and beamed across the void, and it is here that the torrent of data, the whispers from the early universe, are received, processed, and archived. This treasure trove of cosmic information is not the exclusive property of a select few. In a process that is a model for scientific collaboration, Any person from any institution in the world can submit a proposal to use the telescope. Scientists, from Nobel laureates to graduate students, put forth their ideas for observation, which are then subjected to a rigorous and anonymous peer review process. Only the most compelling, the most promising, and the most scientifically valuable proposals are selected, ensuring that the telescope's precious time is always dedicated to pushing the frontiers of human knowledge. The source of the telescope's incredible power, the very feature that allows it to capture the faint light from the dawn of time, is its magnificent primary mirror. It is an immense, light-gathering surface, measuring a colossal 6.5 meters, or just over 21 feet, in diameter. This vast expanse gives it more than 7 times the light collecting area of Hubble's mirror, a difference in scale that represents a generational leap in observational capability. To build such a large mirror and still have it fit inside a rocket fairing, engineers abandoned the traditional single, monolithic design. Instead, they created a mosaic, a perfect honeycomb composed of 18 individual hexagonal segments. The choice of the hexagon was a stroke of design genius. Unlike circles, which would leave unfilled gaps between them, or squares, which would not approximate a circular shape as efficiently, hexagons can fit together with perfect tessellation, leaving no wasted space and forming a single, unified, reflective surface that is nearly circular in its overall shape. Each of these hexagonal pieces of art and science is a significant mirror in its own right, measuring 1.32 meters, or about 4.3 feet, from one flat side to the other. To construct these segments, engineers turned to one of the most exotic and remarkable elements in the periodic table: beryllium. Beryllium is a rare, silvery white metal, and it possesses a unique combination of properties that made it the ideal, and perhaps only, choice for this mission. The selection of beryllium as the base material for the telescope's mirrors was a masterstroke of materials science, a decision driven by the extreme demands of operating in the frigid depths of space. Each of the 18 hexagonal mirror segments began its life as a large, rough blank of pure beryllium, a puck of metal weighing a hefty 250 kilograms, or 551 pounds. This initial block, however, was far too heavy for the mission's stringent mass budget. What followed was an extraordinary process of sculpting, a journey of meticulous and aggressive machining that transformed the solid blank into a delicate, lightweight structure. Engineers carefully milled away excess material from the back of each segment, creating a thin, ribbed lattice that retained immense structural rigidity while shedding an astonishing amount of mass. By the end of this process, an incredible 92% of the original beryllium had been removed. Each mirror segment, now a marvel of lightweight engineering, tipped the scales at a mere 21 kilograms, or just under 47 pounds, while still retaining the strength to withstand the violent forces of a rocket launch and the integrity to hold its precise shape in orbit. But the mirror's true magic lies not in their structure, but in their surface. To transform them from dull beryllium into the most efficient infrared reflectors ever created, they needed a special coating. The material of choice was gold. Gold is an exceptionally poor reflector of visible light, which is why it has its characteristic yellow color. It absorbs blue light. However, in the realm of the infrared, it is a near-perfect mirror, reflecting more than 99% of the infrared light that strikes it. This property made it the only serious candidate for the telescope's coating. The process of applying this golden skin was one of atomic scale precision. Inside a vacuum chamber, a tiny amount of hyper-pure gold was heated until it vaporized. The individual gold atoms then traveled through the vacuum and deposited themselves onto the polished beryllium surface, building up a layer of unimaginable thinness. The final gold coating on each mirror segment is just 100 nanometers thick. To visualize this, a single sheet of paper is about 100,000 nanometers thick. The layer of gold is so tenuous that it is composed of a film only about 600 gold atoms deep. When all 18 segments were coated, the total amount of gold used for the entire massive 6.5-meter primary mirror was a mere 48 grams, or less than 1.7 ounces. It is a mass roughly equivalent to that of a golf ball. An almost impossibly small amount of material spread out to create a collecting area the size of a small house. This infinitesimally thin layer of gold, while a superb reflector, is also incredibly soft and susceptible to damage. To protect it from the occasional stray micrometeoroid or cosmic particle, and to ensure its longevity over the decades-long mission, the gold was given a final, invisible layer of armor. This protective overcoat is a microscopically thin layer of amorphous silicon dioxide, which is essentially a type of glass. This transparent shield is tough and durable, preserving the pristine golden surface beneath without interfering with its ability to reflect infrared light. Once in space, these 18 individual segments had to be aligned with a precision that borders on the unbelievable, so that they could function not as separate mirrors, but as a single, perfectly focused optical surface. The challenge was to make these 18 pieces of beryllium and gold behave as if they were a single monolithic mirror. To achieve this, engineers equipped the back of each segment with a set of 7 tiny, powerful motors called actuators. These actuators can push and pull on the mirror segment, adjusting its position and even slightly altering its curvature. The level of control they provide is staggering. The alignment of the mirror segments can be adjusted with a precision of 10 nanometers, a distance that is 1/10,000th the width of a single human hair. This process of wavefront sensing and control allows the telescope to achieve a perfect focus, compensating for any minute imperfections or thermal distortions. The light collected by this immense primary mirror is then directed toward a much smaller, circular secondary mirror. This secondary mirror, 0.7 of a meter or 29 inches in diameter, is not mounted directly to the telescope's main structure. Instead, it is held in its precise position at the focal point of the primary mirror by 3 long, slender booms. These booms, which deployed in space, are marvels of lightweight, stable design, holding the secondary mirror steady with unwavering precision. The result of this intricate optical dance is a telescope with an enormous light collecting surface. The total polished area of the primary mirror is 26.3 square meters, or 283 square feet. Even after accounting for the small amount of area blocked by the secondary mirror and its support struts, the effective collecting area remains at 25.4 square meters, or 273 square feet, a giant eye ready to capture the faintest whispers from the dawn of time. While the telescope's optics represent a pinnacle of precision engineering, their extraordinary sensitivity would be utterly useless without an equally revolutionary system to protect them. The James Webb Space Telescope is designed to detect the faintest traces of infrared radiation, the heat signature from the most distant objects in the universe. To do this, the telescope itself must be kept unimaginably cold. If the observatory were warm, it would glow with its own infrared light. A blinding fog of self-generated heat that would completely overwhelm the feeble signals from faraway stars and galaxies. It would be like trying to take a photograph of a flickering candle while standing inside a searchlight. The engineering solution to this profound challenge is not a refrigerator or a complex cooling system, but a shield, a passive, multi-layered parasol of epic proportions. This is the sun shield, the most visually striking and one of the most critical components of the entire observatory. The primary mirror, with its 25.4 square meter collecting area, gives the telescope its power. But the sun shield, by creating a zone of permanent, frigid shadow, gives it its sight. This colossal shield is what allows the observatory to passively cool down to the cryogenic temperatures required for its mission. The telescope's long and complex optical path from the primary mirror to the secondary and finally to the instruments culminates in a focal length of 131.4 meters, or 431 feet. This exceptionally long focal length, achieved through the use of the secondary and tertiary mirrors, is what allows the telescope's instruments to capture incredibly detailed and magnified images of the cosmos. The sun shield is not a single sheet, but a sophisticated assembly of 5 distinct layers, each one carefully separated from the others by a vacuum gap. This multi-layer design is the key to its incredible effectiveness. Its purpose is to shield the sensitive optics and scientific instruments from the relentless thermal radiation pouring from the sun, as well as the reflected sunlight and emitted heat from the much closer Earth and Moon. The sun shield is so effective at this task that it provides the telescope with the equivalent of a sun protection factor, or SPF, of 1 million, a number that dwarfs any terrestrial sunscreen. When fully unfurled in space, the sun shield is a vast, diamond-shaped kite, expanding to the full dimensions of a regulation tennis court. This enormous size is necessary to cast a sufficiently large and deep shadow to envelop the entire telescope optics and instrument module. It is a structure of immense scale, yet it is constructed from materials that are almost ethereally light and thin. The 5 layers of the sun shield are fabricated from a specialized material called Kapton, a polyamide film developed by DuPont in the 1960s. Kapton is a remarkable substance, a plastic that possesses an extraordinary combination of properties. It is incredibly stable across a huge range of temperatures, from the searing heat of the sunlit side to the near absolute zero of the shaded side. It is also exceptionally strong and resistant to tearing, a crucial attribute for a membrane that had to be tightly folded for launch and then mechanically tensioned in space. Finally, it is highly resistant to the damaging effects of the high-energy radiation that permeates the space environment. Each of the 5 Kapton sheets is thinner than a human hair, ranging from just 25 microns, or 1/1000th of an inch, for the layers closer to the telescope, to 50 microns, or 2/1000ths of an inch, for the layer that directly faces the sun. To give them their reflective properties, these gossamer thin membranes are coated with a layer of aluminum that is only a few atoms thick. This highly reflective coating serves as a mirror, bouncing the vast majority of the incoming solar radiation back into space. In addition to the aluminum, the 2 layers closest to the sun are also treated with a special doped silicon. This coating, which gives the sunward side a distinct purplish hue, is what allows the shield to radiate away its own heat so efficiently, preventing a buildup of thermal energy. The true genius of the sun shield lies not just in its materials, but in its architecture. The 5 layers are not pressed together. They are held apart, separated by a vacuum. As the sun shield absorbs heat from the sun, that heat is radiated into the gap between the first and second layers. The second layer then reflects most of that heat out into space, absorbing only a small fraction. This process repeats through all 5 layers, with each successive layer becoming progressively colder. The vacuum between the layers is a perfect insulator, preventing heat from conducting directly from one layer to the next. It is this combination of reflection and insulation that allows the sun shield to achieve such an astonishing temperature differential, a thermal gradient that is one of the most extreme in all of engineering. The intricate layering of the sun shield, with each sheet separated by the perfect insulator of a vacuum, is the core of its thermal magic. This design allows for an incredibly efficient shedding of heat. As solar energy strikes the first layer, the vast majority is immediately reflected back into space. The small amount of energy that is absorbed warms the layer, causing it to radiate heat from both its front and back surfaces. The heat radiated away from the sun travels out into the gap between the first and second layers. The second layer, being highly reflective, bounces most of this radiated heat back out into space through the gaps at the edge of the shield, while absorbing only a tiny fraction. This cascade continues down through all 5 layers. Each successive membrane is colder than the one before it, creating a thermal gradient of breathtaking proportions. This engineering marvel allows the sun shield to manage an immense flow of energy. The side of the outermost layer, which is perpetually bathed in direct sunlight, can reach a blistering temperature of up to 380 degrees Fahrenheit, 3 Kelvin, which is a searing 231 degrees Fahrenheit, or 110 degrees Celsius. At this temperature, water would vigorously boil away. Yet, just a few meters away, on the other side of the 5th and final layer, the temperature plummets to a level that is almost incomprehensibly cold. The side of the innermost layer, which faces the telescope's mirrors and instruments, is cooled to as low as 36 Kelvin. This is an unimaginably frigid negative 394 degrees Fahrenheit, or negative 237 degrees Celsius, a temperature far colder than any naturally occurring place on the surface of the Earth. This extraordinary temperature differential, maintained passively, without any powered refrigeration, is what allows the telescope to achieve its scientific goals. The sun shield's ability to create this island of extreme cold is what enables the telescope's sensitive detectors to operate. Without it, the entire observatory would be bathed in its own infrared glow, rendering it blind. The sun shield allows the telescope's primary structure and its near-infrared instruments to passively cool to a stable operating temperature below 50 Kelvin, or negative 370 degrees Fahrenheit. This is the critical threshold needed for most of the observatory's scientific work, a state of cryogenic stillness where the faint whispers of the early universe can finally be heard. Tucked away in the permanent, frigid shadow cast by this magnificent shield is the Integrated Science Instrument Module, or ISIM, the heart of the observatory. This is where the light gathered by the giant golden mirror is focused and analyzed. The James Webb Space Telescope is not equipped with a single all-purpose instrument, but rather a suite of 4 highly specialized and powerful scientific tools, each designed to probe the cosmos in a unique way. The first of these, and in many ways the workhorse of the observatory, is the near-infrared camera, known as NIRCam. This instrument is the telescope's primary imager, responsible for capturing the breathtaking high-resolution pictures that have already become iconic. Its detectors are sensitive to the near-infrared portion of the spectrum, covering wavelengths from 0.6 to 5 microns. It is NIRCam that is designed to carry out one of the telescope's most profound and eagerly anticipated tasks: to detect the faint, ancient light from the very first stars and galaxies that began to shine in the cosmic dawn. By staring at a single patch of sky for hundreds of hours, NIRCam can build up an image of unprecedented depth, revealing galaxies so distant that their light has been traveling for over 13.5 billion years to reach us. It is, in essence, the telescope's time machine, providing the deepest views into the universe ever achieved. Complementing this powerful camera is the near-infrared spectrograph, or NIRSPEC. This instrument does not take pictures in the traditional sense. Instead, it performs the science of spectroscopy, splitting the incoming light from a celestial object into its constituent colors, much like a prism creates a rainbow. This spectrum is not just a beautiful pattern. It is a cosmic barcode, rich with information. By analyzing the specific wavelengths of light that are present or absent, astronomers can deduce an object's chemical composition, its temperature, its density, its mass, and how fast it is moving toward or away from us. NIRSPEC has a truly revolutionary capability that sets it apart from any spectrograph that has flown in space before. While the telescope's passive cooling system, anchored by the magnificent sun shield, is sufficient to bring most of the instruments down to their required operating temperature of around 40 Kelvin, one instrument needed to be even colder. This is the mid-infrared instrument, or MIRI. MIRI is a marvel of thermal engineering, a combination of a camera and a spectrograph designed to see the universe in the longer wavelengths of the mid-infrared spectrum, from 5 to 28 microns. At these wavelengths, the instrument can peer into the dusty cradles where stars and planets are being born, analyze the composition of interstellar dust, and study the faint glow of objects in the Kuiper belt at the edge of our own solar system. However, to be sensitive to this longer wavelength infrared light, MIRI's own detectors must be incredibly cold. If they were at the same 50 Kelvin temperature as the rest of the instrument module, their own thermal noise, their own faint heat signature, would be a blinding glare, completely washing out the celestial signals they are designed to detect. To achieve the necessary level of sensitivity, MIRI had to be brought down to a staggering 7 Kelvin. This is a temperature of negative 447 degrees Fahrenheit, or negative 266 degrees Celsius, just a few degrees above absolute zero, the theoretical point at which all atomic motion ceases. Achieving this extreme cold could not be done passively. It required an active cooling system, a sophisticated cryocooler that acts as a space-based refrigerator. This cryocooler is a marvel of closed-cycle engineering. It uses helium gas, the second lightest element in the universe, as its refrigerant. The system works by compressing the helium gas, then allowing it to expand through a tiny orifice, a process which causes it to cool dramatically. This super-chilled gas is then circulated through tubing to the MyRI instrument, drawing away its residual heat. The warmed gas then returns to the compressor to begin the cycle anew. The entire system is a closed loop, meaning the helium is continuously recycled and is never exhausted. This is a critical design feature, as it ensures that MIRI's cooling system can operate for the entire duration of the telescope's mission. A significant advantage over previous infrared missions that relied on a finite supply of cryogens like liquid helium, which would boil away and eventually run out. The fourth major instrument aboard the telescope is actually a pair of instruments that work in concert: the fine guidance sensor and the near-infrared imager and slitless spectrograph, collectively known as FGS/NIRISS. The fine guidance sensor, or FGS, is not a scientific instrument in the traditional sense, but it is absolutely essential to the mission's success. Its job is to ensure the telescope can point with breathtaking precision and hold that pointing steady for hours or even days at a time. The FGS has two cameras that are used to lock on to pre-selected guide stars in the telescope's field of view. By constantly monitoring the exact position of these guide stars, the FGS can detect even the most infinitesimal drift in the telescope's pointing. It then sends correction signals to the telescope's attitude control system, which uses its fine steering mirror to make microscopic adjustments, keeping the observatory locked onto its target with a stability equivalent to holding a laser beam focused on a single dime from a distance of 40 kilometers or 25 miles. Paired with this incredible pointing system is NIRISS, an instrument designed for unique scientific investigations, particularly in the realm of exoplanet science. It is used to detect and characterize the atmospheres of planets orbiting other stars, searching for the telltale chemical fingerprints of molecules like water, methane, and carbon dioxide, the potential biomarkers of life. The telescope itself, a masterpiece of optics and thermal control, moves through the void in a very particular path. It does not simply sit at the second Lagrange point. It actively orbits it in a vast, looping trajectory known as a halo orbit. This orbit is only semi-stable, requiring periodic, gentle nudges from the telescope's small thrusters to keep it from drifting away. This orbital dance is what allows the telescope to maintain its ideal position relative to the Sun and Earth, keeping its sun shield perpetually aligned while giving it an unobstructed view of the entire celestial sphere over the course of a year. All the data collected by these magnificent instruments, The images from NIRCam and MIRI, the spectra from NIRSPEC and NIRISS, must be sent back to Earth. This is accomplished using a large, high-gain communications antenna mounted on the spacecraft bus. This antenna beams the scientific and engineering data across the 1.5 million kilometer, or nearly 1 million mile, expanse to the giant radio antennas of the Deep Space Network, a set of facilities located in California, Spain, and Australia. The data flows back to Earth at a rate of up to 28 megabits per second, a fire hose of cosmic information ready to be processed and analyzed by scientists. Powering this entire celestial marvel, from the cryocooler to the reaction wheels and the communication system, is a set of high-efficiency solar panels. These panels, which are always facing the sun on the hot side of the spacecraft, generate approximately 2 kilowatts of electrical power, roughly equivalent to the power drawn by a high-end hair dryer. It is a remarkably small amount of energy to power one of the most sophisticated machines ever built. And while the telescope's mission is now expected to last for 2 decades, its ultimate lifespan is not determined by its power supply or the health of its instruments, but by a much more mundane constraint: the amount of fuel it carries to maintain its precise orbit and pointing. A finite resource that is slowly, carefully, and judiciously being spent to keep humanity's golden eye on the universe. The moment the James Webb Space Telescope opened its golden eye, the universe as we knew it began to change. The very first full-color images released to an awestruck world in the summer of 2022 were not merely incremental improvements over what had come before. They were revolutionary leaps in clarity and depth. One of the most breathtaking of these initial offerings was a portrait of a galaxy cluster known as SMACS 0723. This was not just a picture of a few dozen galaxies, but a glimpse into the deep, ancient universe. The immense combined mass of the galaxies in the foreground acts as a powerful gravitational lens, a cosmic magnifying glass that bends and amplifies the light from even more distant galaxies lying far behind it. In the image, the light from these background galaxies is distorted into long, shimmering arcs, ghostly streaks of light that represent some of the earliest structures to form in the cosmos. This image, a composite of multiple exposures taken over 12.5 hours, was the deepest and sharpest infrared view of the distant universe ever captured, a tantalizing preview of the discoveries that were to come. Another of the inaugural images transported viewers to a celestial landscape of extraordinary beauty and violence, the Carina Nebula. This vast, turbulent cloud of gas and dust is one of the largest and brightest star-forming regions in our Milky Way galaxy. While parts of it had been imaged by Hubble, the Webb telescope's infrared vision allowed it to pierce through the obscuring dust and reveal the nebula in unprecedented detail. The image focused on a region nicknamed the Cosmic Cliffs, a dramatic, mountainous landscape where towering pillars of gas and dust are being sculpted and eroded by the intense ultraviolet radiation and stellar winds from a cluster of massive, young, hot stars located just out of the frame. The image revealed for the first time hundreds of previously hidden newborn stars, as well as jets of material being blasted out from their poles, the telltale signs of active star birth. The telescope also turned its gaze upon Stephan's Quintet, a compact and visually stunning group of 5 galaxies. 4 of the 5 are locked in a complex gravitational dance, their structures being warped and distorted as they repeatedly swing past one another. The 5th galaxy, though appearing to be part of the group, is actually a much closer foreground object. The Webb image of this galactic gathering is a masterpiece of cosmic storytelling. It captures vast shock waves created as one of the galaxies, NGC 7318b, plows through the heart of the cluster at a speed of several million kilometers per hour. It reveals streamers of gas and stars being pulled from the galaxies, fueling a burst of new star formation. And in the topmost galaxy of the group, Seyfert 2, the telescope was able to peer through the dust shrouding its core to reveal the brilliant glow of material swirling around a supermassive black hole. Not all of the early targets were in the distant universe. To showcase its versatility, the telescope also observed the Southern Ring Nebula, a spectacular, expanding cloud of gas surrounding a dying star. While Hubble had seen the nebula, it could not clearly see the star at its center. The Webb telescope's Mirror-Eye instrument, with its ability to see in the mid-infrared, was able to cut through the glowing gas and reveal for the first time that the star at the heart of the nebula is actually a close binary pair, with one of the stars shrouded in a dense cocoon of dust. This observation provided a vivid illustration of how interactions between stars can shape the intricate and beautiful structures of these planetary nebulae. Beyond capturing these stunning cosmic portraits, the telescope immediately began its core scientific mission, which included one of the most exciting fields in modern astronomy: the study of exoplanets. The James Webb Space Telescope was designed from the ground up to be a revolutionary tool for analyzing the atmospheres of planets orbiting other stars. One of its first targets was a hot gas giant named WASP-96b. By observing the starlight that filtered through the planet's atmosphere as it passed in front of its host star, the telescope's spectrographs were able to create a detailed atmospheric transmission spectrum. This spectrum, a graph showing how much light is absorbed at different wavelengths, revealed the unmistakable chemical signature of water vapor. While water had been detected in exoplanet atmospheres before, the quality and detail of the Webb data were unparalleled, demonstrating the telescope's extraordinary power to probe the chemical makeup of these distant worlds. This was more than just a technological demonstration. It was the dawn of a new era in the search for habitable planets. The telescope was not only confirming the presence of known molecules, but was also poised to detect the building blocks of life itself, should they exist, in the atmospheres of rocky, Earth-like worlds. Its power extends to the very limits of what is observable. One of its most remarkable early discoveries was the identification of the most distant individual star ever seen. Nicknamed Arundel, from an Old English word meaning morning star. This star is so far away that its light has taken 12.9 billion years to reach us. We see it as it was when the universe was only 900 million years old, less than 7% of its current age. Such a distant star would normally be far too faint to detect, but its light was magnified by a factor of thousands by the gravitational lensing effect of a massive galaxy cluster sitting between it and the telescope. A fortunate cosmic alignment that allowed this single ancient star to be resolved. Building on this ability to see the earliest epochs of cosmic history, the telescope quickly began to shatter previous records, discovering what appear to be the earliest known galaxies, objects that formed a mere 300 million years after the Big Bang, pushing the observational frontier closer than ever to the moment of creation. Its observations are providing entirely new insights into the fundamental processes of star and planet formation. And it has even turned its powerful gaze on the familiar objects within our own solar system, capturing breathtaking images of Jupiter, its faint rings, and its auroras, revealing our own planetary neighborhood in a new and astonishing light. While the James Webb Space Telescope's primary mission is to peer into the farthest reaches of the cosmos, its capabilities have also proven to be revolutionary for studying the celestial bodies closer to home. For centuries, our views of the outer planets of our own solar system were limited to the faint points of light seen through ground-based telescopes and the fleeting, though spectacular, flyby missions of robotic probes like Voyager 2. The planet Neptune, the eighth and most distant major planet from the Sun, has always been a particularly enigmatic world. When the Webb telescope turned its golden mirror toward this ice giant, it delivered an image of such stunning clarity that it surpassed anything seen since Voyager 2's brief encounter in 1989. The images captured by the near-infrared camera provided the clearest view of Neptune's rings in more than 30 years. These faint, dusty rings, named after astronomers who made significant contributions to the study of the planet, are exceptionally difficult to observe. From Earth, they are mostly invisible, lost in the glare of the planet itself. But in the infrared, where Neptune's atmospheric methane gas absorbs most of the incoming sunlight, the planet appears dark and serene, allowing the much brighter, icy rings to stand out in stark, brilliant contrast. The images also revealed 7 of Neptune's 14 known moons, including its largest, Triton, which appeared as a dazzlingly bright point of light, outshining Neptune itself because its frozen nitrogen surface reflects so much of the sun's light. The telescope's ability to see through cosmic dust has not only opened up the distant universe, but has also provided unprecedented views of the star-forming regions within our own Milky Way galaxy. These stellar nurseries, vast clouds of gas and dust like the Eagle Nebula, and its famous pillars of creation, are largely opaque to visible light telescopes. The dust acts as a thick fog, hiding the infant stars that are forming deep within. The Webb telescope, with its infrared vision, effortlessly penetrates this dusty veil. Its images of these regions have revealed a multitude of newly formed stars, still wrapped in their natal cocoons of gas and dust that had never been seen before. These observations are not just aesthetically breathtaking. They are providing astronomers with a much clearer picture of the star formation process, helping to answer fundamental questions about how stars of different masses are born and how their formation influences the evolution of the surrounding cloud. The light from these ancient objects, stretched by the expansion of the universe, provides a direct measurement of the cosmic redshift, which in turn is a key parameter in the models that describe the universe's expansion history. By observing these earliest galaxies and calibrating their distances, the Webb telescope is providing crucial new data points that are helping to refine our understanding of the Hubble constant, the rate at which the universe is expanding. This, in turn, allows for a more precise calculation of the age of the universe itself, fine-tuning the cosmic clock and sharpening our knowledge of our own cosmic history. Perhaps the most tantalizing of all the telescope's capabilities is its potential to search for the building blocks of life on other worlds. By analyzing the light that passes through the atmospheres of exoplanets, the telescope can detect the spectral signatures of various molecules. The initial detection of water vapor in the atmosphere of the gas giant WASP-96b was just the beginning. The ultimate goal is to apply this technique to smaller, rocky planets that orbit within their star's habitable zone, the region where temperatures could allow for the existence of liquid water on the planet's surface. On such worlds, the telescope will search for the telltale signs of not just water, but also methane, carbon dioxide, oxygen, and other gases that could indicate the presence of biological processes. While the detection of these biosignatures would not be definitive proof of life, it would be a momentous discovery, transforming a potentially habitable world into a target for intense further study and bringing humanity one step closer to answering the ancient question of whether we are alone in the universe. The vast stream of data flowing from the telescope is not kept secret or restricted to a small group of scientists. Following a standard practice in modern astronomy, the data collected from any given observation is made publicly available to the entire global scientific community after a proprietary period of 1 year for the observing team that originally proposed the measurement. This policy ensures that the telescope's discoveries are maximized, allowing thousands of astronomers from around the world to mine the rich archive of data for their own research, often leading to discoveries that were not even anticipated in the original proposal. It is important to remember that the stunning images released to the public are not what the telescope sees directly. The telescope's detectors record infrared light, which is invisible to the human eye. The images are composites, created by taking the data from observations made through several different infrared filters. Scientists then assign a specific color, typically from the visible spectrum, to the data from each filter. Red might be assigned to the longest infrared wavelength, blue to the shortest, and green to the one in between. By combining these color-coded images, they create a full color representation that is not only visually spectacular, but also scientifically meaningful, with the different colors highlighting different physical features, such as regions of hot gas or dusty filaments. The engineering that underpins all of these discoveries is a story in itself. To protect its sensitive instruments from the heat generated by its own electronics, the telescope is divided into a hot side and a cold side, separated by the sunshield. The spacecraft bus, which contains the computer, the communications equipment, and the attitude control systems, all reside on the hot, sun-facing side. The mirrors and the scientific instruments are on the cold, permanently shaded side. This strict thermal segregation is essential for the mission's success. To ensure that the beryllium mirrors would have the perfect parabolic shape needed to focus light precisely, they had to be tested under the same cryogenic conditions they would experience in space. This was a monumental challenge, requiring the use of enormous vacuum chambers to simulate the space environment and powerful refrigeration systems to bring the mirrors down to their operating temperature. During these tests, engineers used lasers and interferometers to map the surface of the mirrors with nanometer precision, allowing them to grind and polish the mirrors so that they would warp into the correct shape once they were cold. To maintain this perfect shape in orbit, the back of each mirror segment is equipped with actuators that can be used to make minute adjustments to their position and curvature, a process known as active optics. And the entire observatory, from its tennis court-sized sunshield to its multi-segmented mirror, had to be folded up with incredible precision, like a complex parachute, to fit within the narrow confines of the Ariane 5 rocket Soyuz cone, ready for its dramatic and flawless deployment in the silent vacuum of space. To maintain its unwavering gaze upon a single point in the cosmos, the James Webb Space Telescope relies on a system of profound stability and precision. The primary method for controlling the telescope's orientation, for slewing it from one celestial target to another, and then holding it perfectly still, is a set of devices known as reaction wheels. These are essentially heavy, rapidly spinning flywheels mounted inside the spacecraft bus. There are 6 of them in total, providing redundancy in case of failure. The principle behind their operation is a fundamental law of physics: the conservation of angular momentum. When one of these wheels is spun up by an electric motor, the entire telescope must rotate in the opposite direction to conserve the total momentum of the system. By precisely controlling the speed and direction of rotation of these wheels, the telescope can be pointed with incredible accuracy, all without expending any of its precious fuel. The system is so smooth and precise that it can hold the telescope steady enough to distinguish a single firefly from a distance of thousands of kilometers. While the reaction wheels provide the fine control for pointing, they cannot operate in isolation forever. Over time, external forces, primarily the gentle but constant pressure of sunlight pushing on the vast sun shield, will cause the reaction wheels to gradually spin faster and faster as they work to counteract this solar pressure. Eventually, they would reach their maximum rotational speed and would no longer be able to absorb any more momentum. To prevent this, the telescope must periodically perform a maneuver called momentum dumping. This is where the observatory's small rocket thrusters come into play. The thrusters are fired in tiny, carefully controlled bursts, applying a small external torque to the spacecraft. This allows the reaction wheels to be spun back down to their nominal speeds, effectively dumping their excess momentum into space. These same thrusters are also used for making small corrections to the telescope's halo orbit around the second Lagrange point, ensuring it remains in its gravitationally stable sweet spot. The sensitivity of this magnificent observatory is a thing of legend, a quality often illustrated with a wonderfully evocative analogy. It is said that if a bumblebee were placed on the surface of the moon, some 384,000 kilometers, or 240,000 miles away, the James Webb Space Telescope would be sensitive enough to detect the faint thermal radiation, the tiny signature of heat that the bee emits. While this is a thought experiment, it is a scientifically sound one, a powerful illustration of the telescope's unprecedented ability to detect the faintest traces of infrared light. This incredible capability is the result of its massive mirror, its ultra-cold detectors, and its pristine location far from the interfering heat of the Earth. This level of performance was not achieved overnight. It is the culmination of a monumental effort that spanned more than 2 decades from its initial conception to its launch. The journey was a long and often arduous one, marked by daunting technical challenges, budget overruns, and multiple delays. It required the invention of entirely new technologies, from the processes for manufacturing the lightweight beryllium mirrors to the design of the cryocooler and the complex foldable sunshield. It was a testament to the perseverance and dedication of thousands of scientists, engineers, and technicians from 14 different countries who refused to give up on the dream of building the greatest astronomical observatory in history. The heart of the telescope's sensitivity lies in its detectors, the electronic chips that convert the faint infrared light into electrical signals. These state-of-the-art sensors are so exquisitely sensitive that they can register the impact of a single photon of light. When a photon, the fundamental particle of light, strikes one of the pixels on the detector, it generates a tiny electrical charge. By allowing these charges to build up over long exposure times, the telescope can create images of objects that are billions of times fainter than what the human eye can see. Once these images and spectra are captured and beamed back to Earth, they are not immediately ready for scientific analysis. The raw data contains a host of instrumental artifacts, cosmic ray hits, and other imperfections that must be carefully removed. This crucial task is performed at the Space Telescope Science Institute, where a sophisticated software pipeline processes the data, calibrating it and correcting for any known issues. It is only after this meticulous digital cleaning process that the data is archived and distributed to the scientific community, ready to be turned into groundbreaking discoveries. The telescope's vast primary mirror not only gives it supreme light gathering power, but also grants it exceptional angular resolution. This is the ability to distinguish fine details in a celestial object. The larger a telescope's mirror, the sharper its vision. The Webb telescope's 6.5-meter mirror allows it to see the universe with a level of clarity in the infrared that has never before been possible, resolving fine structures in distant galaxies and the disks of gas and dust around nearby stars where new planets are forming. The optical design of the telescope itself is a sophisticated 3-mirror anastigmat of a type known as a Korsch telescope. Unlike a simpler telescope that might use just a primary and a secondary mirror, the Webb telescope adds a third, tertiary mirror to its optical path. This third mirror corrects for optical aberrations, like astigmatism, providing a sharp, undistorted image over the entire wide field of view of its scientific instruments. It is a design that maximizes image quality, ensuring that the light delivered to the sensitive detectors is as perfect as possible. Even in the seemingly empty void of space, the telescope is not entirely safe from harm. The space around the second Lagrange point is sparsely populated with tiny particles of dust, remnants of comets and asteroids, called micrometeoroids. These particles travel at incredible speeds, and collisions are inevitable. In the first few months of its operation, the telescope was struck by several of these tiny projectiles. While most were harmless, one larger than anticipated particle struck one of the primary mirror segments in May of 2022, leaving a small but noticeable mark. Fortunately, the damage was not catastrophic. Engineers were able to use the actuators on the back of the affected mirror segment to adjust its shape slightly, correcting for much of the distortion caused by the impact. The telescope's performance remains well above its mission requirements, a testament to its robust design. These encounters are a reminder of the harsh realities of the space environment, but they have not dimmed the promise of this extraordinary mission. The James Webb Space Telescope has only just begun its long voyage of discovery. For years, and hopefully decades to come, it will continue to gaze out into the cosmos, fundamentally revolutionizing our understanding of the universe and our place within it, turning the faint, ancient light from the dawn of time into a brilliant new chapter in the story of humanity. And so it remains, a silent, shimmering sentinel sailing through the cosmic night, 1.5 million kilometers, nearly 1 million miles, from home. The story of the James Webb Space Telescope, from its conception as an audacious dream to its intricate unfolding in the void, is a testament to what we can achieve when we dare to ask the biggest questions. It is more than a machine of gold and beryllium, more than a collection of exquisitely sensitive instruments. It is an emissary of human curiosity, an extension of our own senses, pushing the boundaries of sight and understanding to the very edge of time itself. The discoveries we have chronicled here, as revolutionary as they are, represent merely the prologue to its long and fruitful journey. Each day, it collects another flood of photons that began their journey before our world was formed. Each spectrum it decodes is a potential clue in the great search for life. Each deep field it reveals is another page in the cosmic history book, a page we could never have read before. The telescope is not the end of a story, but the opening of a new chapter, one whose contents are still being written in the faint infrared light of the most ancient and distant stars. The universe, in all its silent, ancient majesty, is finally beginning to tell its secrets, and we, at long last, are learning how to listen.